Hello, we're Senior Project Team F41, and our senior project is a vibration isolation system for a scanning tunneling microscope. My name is Stephen De Herrera, and my teammates are Seth Ewing, Jason Behrens, and Ryan McMullen. Our project sponsors are Dr. Gregory Scott of the Cal Poly Chemistry Department, Dr. Eltari Elgendor of the Cal Poly Mechanical Engineering Department, and Tuan Lee, a master's student with the Cal Poly Mechanical Engineering Department. Our senior project is a continuation of Tuan Lee's master's thesis. We're going to be expanding upon previous design work that he's already completed, as well as manufacturing, testing, and validating his design and our own. Scanning tunneling microscopy works by scanning a microscopic tip over a sample and using the principle of quantum tunneling to take images on the atomic level. However, scanning tunneling microscopes are very sensitive and must be controlled within a few angstroms, and so they need to be isolated from ambient vibrations. So Dr. Gregory Scott needs a way to isolate his scanning tunneling microscope from vibrations so that he can obtain atomic resolution images for his research.
All right, so now I want to discuss some of the criteria we used to guide our design. So in order to effectively isolate our system from ambient vibrations, we chose to kind of look at the range of frequencies from 1 to 100 hertz because research suggests that a lot of different vibrations from buildings and from people walking and then just from those kind of sources are in that range. And so that's kind of our goal, is to isolate within that range. Okay, in order to kind of go through the design process, we began by kind of creating some sketches, going through the brainstorming process, and then we actually built some physical prototypes to further guide our design. And then finally, we made a decision matrix in order to rank each idea against some criteria, which led to our final idea, which will be described in a bit.
The final design of our vibration isolation system is pictured on the left. The copper stage hangs inside the aluminum housing and above the magnetic adjustment assembly, which is shown on the right. The magnetic assembly has magnets press fit in the top plate, and it allows for adjustability of the height so that you can change the level of damping of the copper stage. The final design was justified using a series of analyses. A finite element model in Abaqus was used to find and justify the natural frequencies of the housing design. And for the permanent magnet assembly, we used MATLAB to perform an equivalent current model in order to find damping ratios of each of the magnets at different heights. And pictured on the right is the flux density field of one of those permanent magnets.
To justify our mass spring system, we performed time response testing on our system. And so first of all, we performed testing without any damping, and that's shown in the graph as the undamped response, and we found a natural frequency of about 1.14 hertz. Then what we did is we included our magnetic damping mechanism, and then we performed the same test, and we found that the magnetic damping demonstrates viscous damping behavior. And we also found that for a gap distance of 3 millimeters between the stage and the stage and the magnets, we found a damping ratio of 0.09.
Shown here is a video of our vibration isolation system on the vertical shake table in the vibrations lab. In the upper right hand corner of the screen shows the acceleration with respect to frequency, where both axes are shown with log scale. These videos are synced in real time. There are 3 accelerometers attached to the vibration isolation system. One on the support bracket, which is shown in blue and is used to set the excitation of the shake table. Because this one is used to set the excitation, notice throughout the video how it follows the green line, which is our target peak. Another accelerometer is on the top cap of the stage and is also shown in blue and starts below the bracket accelerometer. The third accelerometer is on the main copper stage, which is where the microscope will sit. This is shown with the orange line, and this is what we were trying to isolate. The stage is set to a gap height of 12 millimeters, which, based on our experimental data described previously, will put us at a damping ratio of 0.2. As you can see, at around 2.5 hertz, the stage becomes isolated and drops below the measured acceleration of the bracket and the top cap acceleration. And furthermore, you can see that the orange line is well below the excitation acceleration, and from around 2.5 hertz, it never exceeds a third of the excitation acceleration. As we sweep from 1 to 500 hertz, you'll see that the stage stays isolated, and furthermore, from about 100 to 500 hertz, the stage stays around 6% of the excitation acceleration. The raw data from our test and plotted the ratio of the stage acceleration to the ratio of the excitation acceleration with respect to frequency. And what we found is at 2.82 hertz, the stage enters the isolation region. And within the isolation region, after 4.5 hertz, the largest measured ratio was 0.411 at 17.9 hertz. And then from 17.9 hertz to 100 hertz, the average ratio was measured to be 0.059. So our goal was to isolate vibrations from 1 to 100 plus hertz. And with the data shown, you can see that we are able to isolate from 2.82 hertz through 500 hertz. And therefore, we feel confident that the system will isolate most of the ambient vibration which it will encounter in the chemistry lab. And furthermore, we made the system such that the damping ratio can be adjusted if the isolation is not sufficient.
We would like to thank Dr. Gregory Scott and Tuan Lee, our sponsors, as well as our advisor, Dr. Eltari Elgendorf, for all of his help during this project. We'd also like to thank the Cal Poly Mechanical Engineering Department for making this senior project opportunity available to us and for all of the hard work that went into making it possible for us to continue our senior project during the COVID-19 pandemic. We would also like to thank Dr. Ashraf Al-Barbary for his help with our modeling, as well as Ben Carr and Colin Hart for their help with the shake table testing. Finally, we would like to thank Rob Brewster, Peter Mo Lang, and Virgil Threlkel for their help with our manufacturing. Thank you for watching.